All right. Yeah, I think the mic's working. Yeah. Okay, great. So what I've been talking about in the past two lectures is about the definition of an sl2 categorification, and then about examples. I kind of finished discussing this example of representations in this metric group. So what I want to talk about today is sort of finish explaining why we have an sl2 categorification in this case, and a little bit at least about what that tells us about modular representation theory. Okay, so I'm just reminding you of the discussion we had last time. I look at Sn, I look at sort of Sn for all n, and I have these nice functors that relate Sn for different n. Restriction and induction. And I think people who've thought about these groups realize these are kind of very powerful functors for understanding the representation theory of these groups. And one of the powerful things you can do is I define an endomorphism of these functors given by the Giudice-Murphy elements. And whenever I have an endomorphism, what I can do is look at its generalized eigenspaces. As long as my endomorphism satisfies the polynomial relation, so for example, if the endomorphism space is finite dimensional in the field, I'm always going to have a decomposition like this. Basically, first year linear algebra, but you have to think about it a little more abstract. All right, and I can do this similarly for the induction. We'll talk in a moment about sort of the relationship between this endomorphism of restriction and induction, because of course restriction and induction, they're just random functors, they're adjoint to each other. So I similarly have this endomorphism of the induction, and also looking at the generalized eigenspaces for that. Okay, so these are nice functors, and the claim I want to make is that they give you an SL2 action. But of course, the most basic thing we have to answer for an SL2 action is, what are the objects that have weight k? But part of the data of having an SL2 action is I have to take the representations of Sn for all n, and I have to break them up into pieces depending on what their weight for this particular SL2 action is. So I'm fixing an A. As in the past lecture, everything is happening over a field K of characteristic P greater than or equal to 0. So things are kind of most interesting in the positive characteristic case, but it's useful to also keep characteristic 0 around. And so for a given element of Z mod PZ, which would just be Z if P were 0, I have this SL2 action. And so there must be some property that every, let's say, simple or more generally indecomposable module over KSN has, which is what is its weight with respect to this SL2. And the kind of cleanest description of this, even though it's a little strange, is I have this rational function valued in the center of KSN. So this is a symmetric polynomial in the Giudice-Murphy elements. So this lies in KSN. I might actually want Laurent series in U inverse. Big eraser. This acts on any simple by a rational function valued in K, and the way to find the weight of something is, well, I look at all the simples in its composition series, and my rational function, it's going to be acting by a rational function with coefficients in the field, and I look at its order of vanishing at A, which since it's a rational function, this power of K might be negative. It might have a pole at A. And in that case, it has negative weight. Then it has 0 at A, then it has positive. All right. And if we have a module whose composition factors all have this property, we say that alpha A check of it is K. That's telling us what the weight is under the SL2, EA, and A. And I like this because it's very clean, right? It's obvious that this is a well-defined number for every simple. But it might be a little mysterious to even people who know the representation theory of the symmetric very well. So I want to sort of explain how you connect this back to kind of more usual statistics in the representation theory of the symmetric. Okay, so standard theorem, the simple modules over KSM are in bijection with P regular partitions, where P regular means that there's no part size that occurs P or more times. And there are various stronger theorems you could say, but for my purposes, this is the one you need to know. What's the connection between the partition, the representation, and the usus Murphy's? So if I have this simple, and I have a simultaneous eigenvector for the usus Murphy's, so that means there are some scalars, AI, such that xi times v is ai v, then if this is true, then there must be a standard tableau of shape lambda, such that when I look at the content of the box, which is labeled with I in that standard tableau, I get AI. In characteristic 0, this if and only if simultaneous eigenvectors for the xi's exactly come from the standard tableau of shape lambda. There's one for every standard tableau. We know that that's the dimension of the representation. This is one of the ways of proving that. And in characteristic P, well, it doesn't work out so well, but all of the simultaneous eigenvectors do have this. So for example, just to kind of convince yourself that this isn't crazy, look at the trivial of the sign representation. So what happens? Well, there's only one non-zero vector up to scalar. And what happens? Well, the usus Murphy acts on that guy, and the usus Murphy is the sum of I minus 1 transpositions. So in the trivial representation, it acts by multiplication by I minus 1. In the sign representation, it acts by multiplication by minus I minus 1. And then if I look at, well, so here are the single row, which corresponds to the trivial. Here's the single column, which corresponds to the sign. I know that's actually not true because this guy is P regular, but bear with me. If there's only one standard tableau on this row, and it's 1, 2, 3, 4, etc. And indeed, I'm getting 0, 1, 2 as the eigenvalues of my usus Murphy's. And similarly here in this column, I get 0, minus 1, minus 2, etc. And I actually, if you're going to complain about the fact that this guy is irregular, I shouldn't just say this about L lambda. This is true of the Schwack module of any shape. So I can talk about the Schwack module of this column. And okay.
Is it easy to give an example of not unique for causal characters?
Where what's not unique?
We say there exists a static tableau.
Well, right. I mean, somehow I'm considering contents mod P. So as soon as I have two boxes that have different content in characteristic 0, but they're congruent mod P, then I have this kind of uncertainty. Yeah. Okay, so what does this tell us about this power series? Well, this power series acts by these symmetric functions in the usus Murphy's. So on a simple, shouldn't have written S lambda there, that was a mistake. On L lambda, on S lambda, this is true up to adding a nilpotent element. On L lambda, well, it's going to act by all of those guys in the numerator. I just replace every xi with the contents of the boxes of the Young diagram. And because everything's symmetric, it doesn't matter how I do that. So this top guy is the product of U minus the content of that box squared minus 1. And of course, I'm going to use difference of squares. So U minus this content squared minus 1 is the same as U minus the content plus 1 times U minus the content minus 1. And then in the bottom, I'm going to get U minus the content squared. Okay, so the order of 0 of this guy is just how many times does a given number show up as the content of a box versus how many times does it show up as the content of a box plus or minus 1. And I claim that this ends up simplifying to take the product over addable boxes in the numerator, take the product over removable boxes in the denominator. Okay, so what is kind of clear from that formula I had is the order of 0 at a lambda. This should have been out. It's, well, I get a pole, 2 poles for every box of content A, because I have that guy showing up in the denominator with power 2. So I get 2 poles for every box of content A, and then I get a 0 for every box of content A plus 1 minus 1. And then there was a factor of U, so I get delta of A 0. And I claim that this is the same as the number of addables with content A, number of removables with content A. And the way to convince yourself is look at the 3 diagonals around a removable box. So here, I look at my 3 diagonals, and I have 5 boxes of content A minus 1 or A plus 1. And I have 3 boxes of content A. Right? And the reason this guy is removable is I don't have a box here, and I don't have a box here trapping it. If either one of those were there, this guy would be trapped, and it wouldn't be removable. So here I'm getting 3 times 2 minus 5 is 1. Right? Or I actually should have this the other way around. Minus 3 times 2 plus 5 is minus 1. On the other hand, if I have an addable box, I have to have more of this other diagonals to hold that addable box up. Right? So here I'm getting minus 3 times 2 plus 7 equals 1. So the 3 diagonals around a removable box contribute minus 1, and those around an addable box contribute 1. And if I'm not addable or removable, I get 0. Here I get minus 3 times 2 plus 6, 0. And of course, there's a special exception if A happens to be 0, because then it may be sitting at the very corner, and things will be off by 1, which is why I have to put in this delta function. Okay, this is one of these things where it's better to work through examples and convince yourself, but I just wanted to make that clear, that this is this very common statistic that shows up, the number of addable boxes minus the number of removable boxes, but I like it to say it in a way that makes it a little more clear that it's an invariant. All right. So theorem, EA and FA define a categorical SL2 action where this value of K, the number of addable boxes minus the number of removable boxes, tells you the weight for this SL2. And it's always addable boxes with content A, removable boxes with content A, where content is considered modular. Okay. So what do we want to check? Well, we need to check that EA sends CK to CK plus 1, and FA sends CK to CK plus 1. So I'm going to use this very obvious factorization. I have this product over n. I can break that up as a product over I equals 1, n minus 1. And then one more factor, which is u minus xn, squared minus 1 over u minus xn. But then if I think about this in terms of the functors, this is the O acting on an Sn module. This is the O acting on an Sn minus 1 module. And I'm seeing that the difference between those is a rational function in the last usus Murphy, which is an endomorphism of my function. So when I write this in terms of the functors, this is I apply this rational function O to the guy after I've applied F. And that's the same as applying it before I did F times this function of the usus Murphy. I was denoting that endomorphism of the functor by one. So these are the same equations, but this is an equation in the group algebra of Sn. This is an equation of natural transformations of functors, which comes from thinking about this formula as being applied to a bimodule. Right? Applying Fa is a summand of the bimodule. Ksn is a Ksn minus 1 bimodule. Okay. So in terms of pictures, what this is telling us is if we do the F, and I'm not usually going to write A's on this, but I should sort of remind you guys that this depends on A. And then after I do that, I act with this O. That's the same as if I put O on the other side of the strands, but I have to remember to act on F by this funny power series of events. Okay. So by definition, dot acts by A plus something nilpotent. That's what it means to be the generalized eigenspace for A. So I get that the action of O is u minus A squared minus 1 over u minus A squared times this guy plus something nilpotent. And so this tells us that the order of the pole at A increases by 2. All right, that's what we needed to prove. We went from CK to CK minus 2 when we applied F. You might note here, of course, there's another factor here. I'm only using the factor in the denominator. The factor in the numerator doesn't change whether I have a pole or a 0 at A, but it changes the order of my pole at A plus 1 and A minus 1. So what I'm getting here is that when I apply Fa, well, I also change the action, the weight for the action of the SL2 that corresponds to A plus 1 or A minus 1. So exactly what would happen if A and A plus 1 were connected by a single edge in the Dickin diagram. So I'm seeing that these two copies of SL2 interact like the two SL2s and SL3. All right. And a very similar argument shows the same thing for E. I just look at this equation and I move this factor to the other side of the equation. All right, so E increases this by 2. That's what we needed to check. We act on the right categories. Any questions? So if you want to think about this in terms of boxes, right, what's happening here, Fa adds a box with content A. So it destroys an addable box and it creates a removable box, right? And if you think about A plus 1, what's happening here is when I add a box of content A, I either destroy an addable box or create a removable box for things of content A plus 1 and A minus 1, but only one of those. And again, that's one of those kind of draw some pictures and convince yourself. All right, I need to check that my EA and FA are adjoint pairs.
Sorry, that's
yeah.
Going back one, when you said how the two A and A plus 1 interact, I somehow would have expected it to increase the order at like A plus 1 by 1.
Yeah. Right. So this numerator vanishes to order 1 at A plus 1 and vanishes to order 1 at A minus
1. Thank you.
Yeah. Okay. So the next thing we need to check is that these guys are an adjoint pair. Well, we start with the fact that we already know that res and ind are an adjoint pair. All right. And they're adjoint in both directions because we're talking about finite groups. So we can draw purple lines for res and ind. This is to distinguish between black lines, which I'm going to use for EA and FA. And we can think of the use of Murphy as like a dot on this purple guy. And then we define its mate or its dual. I think I missed when Alistair defined this, so I don't know which word to use. But whenever we have an adjunction, we can take an endomorphism of one of the functors, and we can do this trick to get a dual endomorphism of the other functor. And you can check explicitly, this is a good exercise in thinking about adjoints. that if I have an element of the group algebra of some group G that commutes with the group algebra of a subgroup, that gets me an endomorphism of the restriction function. And so you can apply this algebra to get a dual map of induction. And Owen and I did this calculation yesterday. We confirmed it's you do right multiplication by the same element on when you write your element of the induction G tensor n. And exactly the fact that this guy commutes with K of H makes sure that this is well defined. All right, so the fact that EA and FIA are adjoint, in fact, this makes clear they're biadjoint, is just basically some general nonsense about duals. So one helpful way to think about this is like this black strand, A, this is the image of some projection on the full restriction functor, and the projection to FA is taking the mate of that projection. And you can convince yourself of this. So this is actually a general result, that if you take generalized eigenspaces of a natural transformation of a functor, those are going to be adjoint to the generalized eigenspaces of the dual acting on the adjoint here. That's just kind of some general nonsense. Now comes a really kind of important part, which, you know, because I'm short on time, I'm not going to justify in a lot of detail. But this is really kind of the heart of why this is so powerful. So I need to define these endomorphisms Y and C. So Y is easy to define. I just look at the Eustace-Murphy and I say, oh, but I want Y to be nilpotent. So I need to subtract the scalar A. Again, because we're on the generalized eigenspace, Xn minus A is nil. So you should compare this to what Pong was doing in her talk, where she was looking at the action of the center. And again, the action of the co-invariant algebra is actually the nilpotent parts of the elements of the center of the universal developing algebra. She was picking a block, so that was fixing what scalar every element of the universal developing algebra acted by. But it was, you know, that scalar plus something else. All right, and this is just kind of the picture. We can pick some basis, right? A's along the diagonal and some junk up above, and I just turn the A's on the diagonal and remember the junk up above. All right, and I have to define C. And because I'm short on time, I'm not going to try to explain this in great detail. It's just this formula. Take Sn minus 1 plus 1, and I multiply it by the inverse of Xn minus 1 minus Xn minus 1. I should at least comment, why is this well defined? Because I'm looking at the A eigenspace both of Xn minus 1 and of Xn. Right? So both of these guys act with the scalar A minus plus something nilpotent. So this guy is something nilpotent minus 1. Something nilpotent minus 1 is always invertible by the geometric space. Well, here I even have my formula, right? So Xn minus Xn, Xn minus 1 minus Xn on F squared acts by Z, or sorry, an E squared. Acts by something nilpotent. So I write out this geometric series, but eventually all the higher powers are going to be 0. So this right-hand side is well. All right, and the main interesting thing to check is, why does this guy square to 0? Since I'm tight on time, you can all refer to the notes for how you do this calculation. Sort of one of these fun calculations to do once. It's using, kind of in a really key way, these rules for how Eustace-Murphys commute mass transpositions. So at the end of the day, the nice thing is you get this sort of rule for how this particular Oh, you're gonna, okay, good. Had a moment there of like, are people not seeing this? So this particular fraction commutes past Sn minus 1 in a nice way. And the thing to note here is here I have Sn plus 1, here I have Sn minus 1. So when I take this square, I can rewrite it as Sn plus 1 times Sn minus 1 times this rational function. Well, it doesn't matter what this rational function is, this product is 0. All right, and then one also computes how the uses Murphy mutes past this guy. This is again kind of not too terrible calculation. You know what you're trying to get to. It's just apply the relations for how x's and s's commute. All right. But there's an important lesson here, which I probably should have emphasized last time, but I didn't, so I got to do it now. Which is when I take a big power of ek, or the same thing applies to fa, it has an action of nh, which we saw last time is a matrix algebra. Having an action of a matrix algebra on something is really powerful because it tells you that the thing it's acting on is the sum of a bunch of isomorphic objects. The number that they show up is the rank of the matrix. Right? I look at the projections corresponding to the images of all the diagonal matrices, 1, 1 on the diagonal, and all of those are isomorphic because they're off diagonal matrices that give me the isomorphisms. So this power is actually the sum of k factorial isomorphic objects. And so I can take the image of one of these, that gives me a subfunctor, and this is what we call the divided power functor. So we use round brackets k. This is the divided power. It's a really powerful thing, but there's not just e to the power k, there's this piece of it, that e to the power k is k factorial copies. All right, so we've checked A, B, and C. There's one important thing left to check, which is why do we get that when we do EAFA and FAEA, those are almost the same, but there's some weird number of other copies showing up that depends on the statistic alpha check. So the stuff I've done thus far didn't require anything about this alpha check. This is where this alpha check and the difference between addable and removable boxes suddenly becomes important. So first, to get a feel for how this works, let's do this in characteristic 0. We should expect it to be a lot easier in characteristics. And indeed, right, in characteristic 0, there's at most one addable or one removable box of content A, or there might be none. So there's sort of 3 possibilities here. No addable or removable box, addable box, removable box. All right, and these are the same pictures from last time. So what happens if there's an addable box? Well, that means when I apply FA, I get lambda plus that addable box. And when I apply EA, I remove the addable box. And I get that S lambda gets sent to S lambda. On the other hand, when I do, why is this weird? When I do them in the other order, I get 0. So we see why this guy has to have weight 1. If you just kind of look at do this case, it's very easy because spec modules always get sent to spec modules for 0, and it tells us immediately what the weight is. So if I have a removable box, the opposite happens. FA acts by 0, because that tries to resolve that version. That tries to add a box, and it can't because there's a removable box. On the other hand, EA removes the box, and then FA adds it back. So that's a spec module to the spec module. So we're just checking explicitly for each spec module that this equation works. But it actually always just says EA FA or FA EA might be the spec module. And if that's the case, you have to add in a copy of the spec module on the other side by hand. All right, and then finally, if there's not an addable or a removable box, then both of these guys are 0, and the equation holds. Okay, so this confirms that we have the SL2 actions in characteristic 0. Now let's say something about characteristic P. So I'm mostly going to kind of wave my hands here. In characteristic P, we only need to check this on projectives. So if I have projectives, I can write my K as the quotient of a complete DVR, that residue field, and I can deform the projective over that DVR. And to check that the projectives are isomorphic, it's enough to check that it's true after tensor compression. If that's true, probably that's right. Okay, so the key thing is, if I apply, whoops, I didn't do these things. If I apply EA to a projective, and then I deform that in tensor with the fraction field, that's the same as if I had deformed to the fraction field and applied, well, not just one EA, but EB for all B in this coset, and I wrote the wrong coset, of course. Okay, so what's happening here? I'm applying induction, and I'm looking at eigenspaces mod P in FP. So I get an eigenspace for every element of FP. Well, if I deform and take the eigenspaces there, I could get any integer that reduces to that class mod P. So I have to think about all of them together. But this is always kind of what's happening over FP, is that I have these functors that correspond to different integers mod P, and then suddenly mod P, they get stuck together. They get funny extensions between them, I can't tell the difference. But for just checking the right isomorphism, I just need to check that I need P's in all of these. Right? Everywhere there's Z plus A plus Z, I mean plus PZ. So I just need to check that if I take this in characteristic 0, the sum over a whole coset for P times Z, then those commute in the right way. Okay, this reduces to a characteristic 0 computation, and we've already done that. So now I'm looking at a spec module in characteristic 0, but I'm looking at adding all boxes of content that's congruent to A mod B. Well, if I add boxes and then removing those, right? This is add boxes and then remove them. This is remove boxes and then add them. If the contents are different, then the order doesn't matter. I add a box over here, I can still remove one over here, and it doesn't matter which order I did it. So the only terms that matter are when I add a box and then remove it, or remove a box and then add it. So the difference between the two sides, again, comes down to the difference between the number of addable boxes and the number of removable boxes, which was exactly this alpha I check, or alpha A check of my module. So since this difference is exactly alpha A check, that's what we needed to check. Okay, we're exactly getting this equation. This is a kind of dissatisfying proof. I don't really like it. There is a much more conceptual proof. I mentioned the existence of this Heisenberg category before. So So you can really much more explicitly prove this and prove sort of by hand that the morphism or that wanted to be an isomorphism really is an isomorphism. But as I say, that's like if we had another reading version. I mean, it's sort of very elementary, but it involves a lot of like computation models, which, you know, it would have been fun, but I guess the next workshop maybe we'll do that. But the cool thing about this is you can prove a much more general theorem that applies in a ton of cases. You can do them all at once. So somehow this argument about, you know, I was basically checking that the right thing happened on the Burton. You have to keep checking that over and over again for all the different examples. Much better to have one conceptual proof that works for all. I'll note here there's an exercise, sort of very enlightening to do sort of small cases of this for like F2. Let's see what's going on. Carefully thinking about what I actually have time to cover. These SL2 actions, I feel like it's worth noting. I mean, somehow the things we're going to do, they mostly just require thinking about them one at a time. But of course, we already talked about this SL3. There is some relationship. So one nice way to think about this is think about the Grothendieck group of projected modules over all the KSNs for all n. And I don't really need to tensor this with C, but it's a little bit nicer. Maybe I do. So what I've shown you is that there's an SL2 action on this Grothendieck group. There's one for every A in Z mod P set. And if you look at how these interact with each other, exactly what you get is a copy of SLP, affine algebra for SLB. And you know, somehow the main thing to note is how the weights change as you apply F. And you exactly get the entries of the Cartan matrix for SLP hat. There's a negation of the Cartan matrix because I put F. A decrease by 2 if A and B are the same, an increase by 1 if A and B are adjacent and not in P equals 2. Doesn't change at all if they're not adjacent. And in this weird case, P equals 2, they change by 2, and there are 2 different elements of that. This is exactly the Cartan matrix of SLP. And one nice thing about this is now I can give a very nice description of this Grothendieck group. So if I look at K0, that's just a copy of K. There's one simple module over it, which you can think of as L empty set, empty Young diagram. And if you look at this guy and compute how it acts for all the SL2s, for A0, right, when I induce this guy, I get K of S1, which is also trivial. The uses Murphy acts by 0. So F0 is the induction, all the other F's are 0. And all the E's are 0, because those take you to S of -1. So what that's telling us in Lie theory terms is this is a highest weight vector whose weight is what we would call lambda 0. It's fundamental for SLP. And it turns out the sum of Grothendieck groups is actually an irreducible representation over SLP. You can think about all kinds of interesting stuff about the symmetric group, but thinking about this particular group. For example, like this tells you what combinations of sizes of boxes can you have of contents. Can you have a partition with those contents? Well, it's exactly the ones that correspond to non-zero weight spaces of this SLP hat. And maybe the thing I will emphasize here is if I look at the class of the Speck module or also the symbol corresponding to lambda mod P, then this is always a weight vector, right? And I told you what its weight for each one of the individual SL2s is. If you think about what that means I take lambda 0 and for every box in the Young diagram, I subtract a copy of the root corresponding to that box. That's really what those formulas I wrote before were telling me. It's kind of a usual description of this part on where the coordinates, sort of important coordinates, are the difference between the numbers of boxes. Consecutive things. So they're often written as TIs. These are the number of beads on each runner of the abacus. If you like. These TIs can be, right? This is the statistic that was the addable minus removable boxes. You can also write it in terms of these TIs. Whew, running pretty low on time. I don't know, when did I start? Did I start at 30 past?
No, you started at like 35 minutes.
Okay, so I can go maybe 10 minutes more. So, because I wanted to get to an actual application. And this is all kind of, I think this is really cool, but if what you care about is symmetric groups, what does this tell us? Well, there's this kind of incredible fact that if I start with a simple module, this is all in any characteristic, in particular characteristic P, positive. If I apply EA to L or FA to L, those have a unique simple quotient and a unique simple sum. And those are actually isomorphic, which we denote EA twiddle of L and FA twiddle of L. And I mean, I'm not going to have time to prove this, but the easiest proof of this is actually a completely general fact about sl2 categorifications. So this is proven in a slightly roundabout way in Chuang-Rouquier's original. But this is just a general fact about sl2 categorifications. It always happens. So just to think about a few examples where this can happen. So if I look at K of S1 and I do induction, I get the group algebra of S2. So if P is not equal to 2, I get the trivial plus the sign. That's f of 1 and f of minus 1. So those are simple, and indeed the theorem works. If P equals 2, then just f of 1 and f of minus 1 are the same now. Right? So just have f of 1, that's the whole group algebra. And well, the whole group algebra I can write as polynomials in the unique non-trivial element, mod s minus 1 squared. So now I'm getting a ring where the ring is indecomposable as a module over itself. And indeed, it has a unique simple sub and a unique simple quotient, and those are isomorphic. So the kind of magic thing is that this always happens. And this is sort of a dumb special case, but this always works out. Let's see. So, yeah, sort of another example that I like quite a bit is if you take a trivial representation of S2. So when you induce that, right, that corresponds to having this guy. And so they're addable boxes with contents 2 and minus 1. So if P is not 3, then I get F2 and F minus 1, both of which are simple. So F2 is the trivial, and F minus 1 is the unique irrep for S3, which is not the trivial, it's the unique two-dimensional. On the other hand, if P is equal to 3, then actually F2 of K is indecomposable. It's an extension where that has a trivial is the quotient, the trivial is the sub, and then a sign sitting in the middle. So basically, if you look at the two-dimensional guy over S3 and you reduce it mod P, it turns into an extension of the sign in the trivial, and which order the extension is depends on exactly how you chose the integral basis. So it can kind of either be this part, or it can be this part. Note here, there's unique sum, there's unique quotient, and they're the same, they're the trivial. All right, so we mentioned before, irregular, there's bijection of simples over KSN with irregular partitions. And there's an explicit description of what is the unique simple quotient or sub of EA and FA applied to L. That's the standard crystal structure of P regular partitions. Running a little low on time, but I really like this crystal structure, so let me try to explain it. We look at lambda, the actual Young diagram. We put an open parenthesis over every removable box and a closed parenthesis over every added box. Hopefully I did this right. So you look at those, and some of those parentheses are going to cancel. You ignore all the canceled parentheses. And what FA does is it adds the box that corresponds to the rightmost uncanceled closed parenthesis. So this is the unique way to flip a closed parenthesis to an open one that doesn't make any cancelings. And similarly, EI, I had to switch from I to I, sorry about that. What EA does is it removes the box for the leftmost uncanceled parenthesis. Sorry, I just had this like compulsion the whole time I was doing my notes to switch from A to I, which maybe I should have just given into. And I think I did at some point, which just made things worse. All right, but it's always that I flip a parenthesis that doesn't create any U cancellations. That's always the rule. And if there are no uncanceled ones, then FA and EA, people would say they go to 0. Like what's happening here is that applying that functor to the simple gives you 0. I kind of like to say they're not defined, but it just kind of depends on your preferences. So for example, in P equals 2, I have 2 addable boxes of content 1. So I have 2 closed parentheses. F1 flips one of them, right? So this is kind of the first case where I have 2 boxes of the same content that I could potentially add, and I have to decide which one I do. And this rule tells me, oh, I do this one, but add the box. And then if I do this operation again, well, right, the cancel parentheses never change. So it's just, if I go down the sort of root string, I'm just flipping the parentheses one at a time. So now I flip the other one. Whereas if I started with this column, I have canceling parentheses. I have a removable box, then an addable one. And so this operation just isn't defined. Okay. All right. And you might wonder what sort of thing corresponds to this. There's also sl2 actions on modules over the Schur algebra, and I can interpret this guy as a module over the Schur algebra, and this is telling me that F1 and E1 kill that simple module over the Schur algebra. So these guys are inverse when they're defined. You can check that these operations preserve P regularity. So you sort of saw what happened here, right? I was kind of tempted to add a box that would have made me not too regular. And this rule said, no, add this one and save me 2 regular. So that's sort of always what this rule does. And I'll just note, there's actually always, if I have a P regular partition, there's always a removable box. So all of these guys are connected by these operations. You can go from any P regular partition to any other one by a chain of these guys. And this ends up being the crystal graph of that representation we talked about. So for example, for P equals 2, here's my crystal. This tells me not precisely what the induction and restriction of these simple representations are, but what the most salient composition factor is. Yeah, I should just mention, there are lots of extensions of this, and it's always this crystal. If you're used to thinking about crystals, this is the tensor product rule, for the defining representation of C2, and it's just always, everything is for each individual SL2, it's a tensor product of the defining of the two-dimensional reps, and you use that crystal. So maybe I'll just skip this. If you know, you know. So what's an interesting application of this? Now I have like -1 minutes now, but this is so nice, I gotta tell you. So if I have L lambda, then an obvious thing I can do is I can tensor it with the sign representation. The result is simple. So the result is L of lambda star for some other p regular partition. So in characteristic 0, of course, this is transpose. But the transpose of a p regular partition is not p regular. So that's obviously not what this operation is for small primes. On the other hand, think about what tensoring the sign does. It's the action of the use of Murphy's. It negates it. It just takes how xi acted and it multiplies it by -1 for all I. So what this tells us is this star operation commutes in a really nice way with the crystal graph operators. Right? If I induce and take fi and then take star, that's the same as if I had started with the star, induced and taken the eigenspace for -i. And because I can connect all of the partitions with these crystal graph operations, there's a unique operation lambda star that satisfies. So for example, this is what happens if, okay, p equals 2 is boring, so it's the identity. If p equals 3, then what happens? So here I started the identity, I get the trivial and the sign, and of course those are sent to each other under this. And I see that because the trivial is gotten by applying F1, the sign is gotten by applying F2, and 1 and 2 are negatives of each other. So here's the first interesting one, right? If I apply F2 and F1, I get these guys, so these have to swap under tensoring with sign. And you get progressively kind of further and further away from taking transfer, right? It has a little bit of this flavor of being a little bit transposy, but it's kind of weird. You can even get situations where you have partitions, which are both the partition and the transpose are 3 regular, but they aren't sent to each other under tensoring the sign. This guy did, this is the sign representation, and this is the defining reflection representation tensored with the sign. This is a weird solid. And at least as far as I know, this was the first way that this was actually constructed. It was rigorously proven what this tensoring with sign did. There was a long-standing conjecture called the Molyneux conjecture, which had given a different combinatorial description of this. If I understand correctly, basically, Kleshchev noticed that there was this description of tensoring with sign. That was kind of the key to proving that Molyneux was actually right. Okay, I'm out of time, but why does this crystal structure work? Because all SL2 categorifications are built out of these simple ones we defined earlier, and this theorem works in the simple ones, but in a not totally trivial way. In every weight, there's unique simple, and when I apply induction restriction to it, well, I don't get something simple, but I get a copy of the cohomology of a projective space. So it has a unique simple quotient given by modding out by all the positive degree stuff, and it has a unique simple sub corresponding to the fundamental class. So this is actually something about Poincare duality on CPN. All right, and then basically Chuang-Rouquier tells us, well, every SL2 categorification is built out of copies of this guy, and it's built in such a way that this property carries. Particularly, you can always construct this simple, right? The last power of this before it's 0. That makes sense in any SL2 categorification applied to a simple. And what's always going to happen is the last power of this guy before it's 0 is a map from the induction to itself, from, let's say, FA applied to my simple to itself, whose image is the unique simple sub And so, you know, what it's doing is the co-image is the unique symbol. So it's exactly realizing that there's a unique symbol sub, there's a unique symbol quotient, isomorphic via this map from the induction to itself. All right, I'm out of time. 5 minutes over, so I will